Well, I'll just start by thanking the many people that have put together parts of this talk or enabled me to do this work, and so particularly the RRAP. So I lead the environmental interventions sub-project within the RRAP, and so there'll be results from that, which include work from others. Also, we've used the eReefs model quite a lot. So a lot of you will know that I've spent years working on this eReefs model. There's a big team down in Hobart who've also worked on it, and the output there is that's an output just showing the bleaching in 2016 that the eReefs model is predicting, and I'll come back to that slide in a bit. Earlier yesterday, a few people introduced their, I guess, early experiences of the reef. This doesn't quite count, but my first experience of coming up to far north Queensland was as a heat transfer engineer. I went over to Queensland Nickel to improve their recovery of heat in their processing. So perhaps not the inspiration that some of you had, but actually quite relevant for today's talk. And so I also hope to, I guess, I think that the engineers will be some of the people who, of course, end up solving this problem. I hope this talk works for an engineer like that, so that's keen to solve the world's problems. And actually in the background is Joe. Joe was the site engineer. He was the one that actually went and fixed all the things following my suggestions. Of course, there'll be lots of jobs available in construction should we go ahead with many of these interventions. So I hope in some senses this talk is also for him. Joe and I spent lots of time going to mine sites around Australia, a few wild stories, but probably not for today. Okay, so the question is it feasible and worth altering the temperature and light stress on the GBR? Now, of course, I'm only going to answer the beginning of this question. Whether it's worth it, that's a question that spans, not just the engineering solutions, it spans the values that we have for the reef and everything, and so which of course everyone in this audience knows, and so the RRAP is taking that on, and of course many of you in here as well. So I'm just going to concentrate on feasibility, and in particular I want to build some tools, and we're just in the process of doing it, that will help practitioners to scope out and eventually, I think, optimise interventions. And so here's just one piece of inspiration for me. So I remember when I first started in aCSIRO back in 2000, and they were doing what they called wind prospecting. They were looking for the best sites in Australia to put wind farms. Okay, and of course that knowledge then got put into databases. This is the Australian Renewable Energies database. From that, engineers were able to go and energy companies were able to go and site their wind farms. They didn't have to go and prospect, if you like. So I feel my role is a little bit the same in this talk, that what I'm trying to do is look at different parts of the GBR where interventions might be more or less successful, okay, so that takes away some of the work for the practitioners to then go and work off the reefs that are where it's going to be most effective. So let's see how we go. Okay, so just starting with temperature, so possible interventions, and you'll hear more of these through the day, include cold water injections, enhanced vertical mixing, shade cloths, reflective surface films, marine cloud brightening. Range of either putting cold water directly on there or reducing solar radiation, or bringing water from the bottom. So to look at what how these work, I'm going to use the eReefs model. So just a very quick introduction to it. So it's a coupled hydrodynamic and ecological model, or biological model, so we can use it for some of the coral responses. But for the moment, we're just going to use the hydrodynamics of it. Of course, it's forced by winds and solar radiation, all this meteorological forcing, river flows, etc. And so just to give you a quick schematic of the 1 kilometre model working. So on the left here, we just have temperature. It's quite cool at the moment. I've just downloaded this last night. It runs in near real time. And just to give you an idea of its skill, on the right, I've just got the temperature of a couple of different configurations in red and green. We're going to be using the one in red compared to some in situ observations showing that it certainly is skillful at the seasonal scale, and right down to the hour scale, it's pretty successful. So In that model, of course, you have a lot of processes affecting the temperature of the water. These include solar radiation, how cloudy it is, solar angles, orbital cycles, etc. Of course, we've got a lot of thermal energy coming in from the Coral Sea, Torres Strait, even from the rivers. So the question is with these huge fluxes of temperature, are there interventions that we can do that will actually alter the temperature? Okay, so my first task was to look at the scale of the whole GBR, and so one way that we wanted to do this, and so this is using the 1 kilometre model, which I'm going to, in a moment, say is not good enough, we need to go high resolution, but for the moment, looking at the 1 kilometre does give us an insight. So looking across the whole GBR, where are the most efficient regions to achieve cooling? Okay, and one way to do this was to look at the temperature in the model between night and day. Okay, because obviously at night time it's managed to cool off, right? So of course that's the natural atmospheric flux, but it gives us a sense for that scale of flux, what temperature difference we can get. Okay, and so what you clearly see, and I think this will be an insight that will play out, is that it's the central GBR. If you look on the left here, that's the temperature difference between day and night. Okay, and the bluest is minus 0.25 degrees. It's colder at night. You can see you get a much bigger, at that broader scale, cooling overnight. Okay, and so the reasons for that essentially relate to, I guess, the tidal influence. Because when you're in the Torres Strait or down further south off Gladstone, large tides, that causes a lot of vertical mixing, and so therefore you have a well-mixed water column, and if you're going to cool the water, you've got to cool the full depth of the water in the inshore regions. Whereas when you're in that central area, you're going to, because there's less drag on the bottom with the tides, then you get less vertical mixing, and you have less, so therefore there's less water that you have to cool. So I wonder if we'll find our interventions that are working off a temperature difference between the surface and lower to inject water, and just to have a smaller region to cool will work better in that central region. Okay, so but we need to get to finer scale, so just to quickly introduce the relocatable model we have. So in eReefs, we have this 1 kilometre model, and you can see actually the output of that is the grey arrows and the big boxes on the outside rim of it. And what that does is it forces a higher resolution model. So that's the smaller arrows, the blacker arrows are more densely packed. And so that gets down to 200 metres. And this is Davies Reef off Townsville. And you'll see this again just because the moon phases changes. Obviously, tidal muscle. I've got the moon down there in the bottom left. You can see the change in surface elevation through the day, got temperature, etc. You're going to see a few more of these, or at least the outputs of them. Just to introduce it, so this is a product which is available for people to go and use. So it's actually a web interface. You've just got to click on boundaries, add a few, you go and click on a map, you set the boundaries. This will automatically generate a high resolution model. It's not just actually the high dynamics, it's the whole eReefs BGC as well. And you'll get an animation just like this at the end, but you also get the full data that you can then download. You can even run it yourself if you're doing an intervention and look at what happens if you put, inject cold water on it. You'll have to be a bit more of a skilled modeler to do that. But this is a tool that's available through the eReefs project. If you're interested, please give me an email and we'll get you set up. So I'm going to use this and you'll see how useful it is. Okay, so now, so I wanted to think about two different ways of having cooling. Okay, so the first I'm going to call site cooling load. So this is if you're a very small patch and the water's coming past you, and you need to cool the water upstream of you, of course, in order to have it the right temperature at the location that you want that patch to survive, right? And so the amount of energy that you're going to need to extract from that flow is proportional to the velocity, of course, constant the heat capacity of the water, and density. The temperature difference you want to achieve, maybe it's 1 degree, maybe it's 1 degree above the climatology and you want to cool it by that amount, and of course the depth of water. Okay, so we're going to call this the site cooling load, and when we think about this one, think about it as water coming past your patch, but you're never going to see it again. So you've got to do this one-off cooling to it. So that's a really tough task, okay? The second concept I want to introduce you to is if you try and cool a whole reef, okay? And so now, of course, the water's going to move around the reef, so you've got a bit of a retention time, okay? So it's going to be less cooling per metre squared, but of course you've got to cool a whole reef, or at least a whole larger area. So how am I going to quantify that? Because now what I need to know is how often water is being taken into and out of that control volume, if you like, that's water above the reef. Okay, so I've got an equation, but better than that, I've got a demonstration of how I'm going to do this. So just to come away from the mic, so what we're going to do is we want to trace how long water sits above a reef. Okay, so what I'm going to introduce into the model is what we call an age tracer. Okay, and so I want to give you the dynamic of that age tracer. So it's like heat, which gets moved across the reef. Okay, but the way that we're going to do this age tracer is it takes a value of initially 0 everywhere. Okay, and then imagine that I've got a reef that starts here and finishes here. Okay, what's going to happen is as the water gets moved over, once it gets onto the reef, it starts to age. Okay, so it's gone 1 hour, 2 hours, 3 hours, okay, and then it's come off the reef. It actually holds that 3 hours because the tides come back, so now when the tide comes back this way, it's still held that 3 hours, okay, and then it's going to age 4, 5, 6, and maybe it falls off the reef here and never returns and it heads off somewhere else into the coral sea. Okay, but you get the sense that this age tracer is tracking how long water sits above a reef. Okay, and so that's the time scale I have to cool the water. Okay, and so you're going to see this age tracer a bit. And so the equation that describes this cooling load there with the age tracer being this tau symbol is there for those who are interested. Okay, so now to take you through this slide. So I've got 4 panels here. On the top left, so this is Davies Reef again. The top left I've got the reef, and this is the temperature above the reef. We're in 2016. You can see the time going forward. You've got the moon over there to help you, and the area of the reef, and depth contours of 10 and 20, 5 and 10 and 20 metres. Okay, we've got the temperature anomaly. So that's how much we are above the climatological maximum. So this is what we feel we shouldn't go above. Okay, and then on the bottom left, we've got this age trace that I was talking about. And so you can see, and you've got the currents as well. And so you can see this age tracer being moved around. You can see that while it's over the reef, it gets older, but when it gets taken off, it moves away. And the fresh water that comes onto the reef takes time to get to that age. Okay, and so you can see that for Davies Reef, this age tracer, because the tidal excursions take it right across the whole reef, the tidal excursions, because they take it across the whole reef, the longest the age tracer ever gets to is about a quarter of a day. Okay, the residence time is really short. So if I'm going to cool the water above Davies Reef, at best I'm going to have to cool it every 6 hours. Okay, which is a fairly impossible task. And so that's why you see the cooling. So I've also got the winds there, which sometimes affect push the water off, more so in other reefs. So anyway, and so then I've got at the top I've got the Psych cooling load, and then I've got the reef cooling load as well. So when it comes to the reef cooling load, I've scaled it actually so that the reddest is equal to the solar radiative forcing. Okay, 1,353 watts per metre squared. That's what, if you're at the top of the atmosphere with pointing it straight at the sun, that's how much you would receive. So it gives you a sense of the amount of cooling that you'd have to achieve. If it's gone red, that's equal to or more than what the sun is. Okay, so on Davies Reef, this is looking pretty difficult, and the Psych cooling one is even worse than. I've scaled that by an extra factor of 1,000. Right, so this is 1,000 times the sun is the energy that you'd need to apply for the Psych cooling. However, you're applying that just in the 1 metre upstream of the reef. So if you applied it over, say, a kilometre, then it would only be 1,000 times. But that means you might have to shade the water for a full kilometre before it came over your site to actually get the cooling you need. So site cooling is a difficult task. Okay, this is Davies Reef with a short residence time. Let's now go to Arlington Reef, much bigger reef. Okay, this one's off Cairns. And so, so now it's interesting, you see so as we go through this simulation, you'll see that the age tracer will get quite a bit older, because there's a longer, it's a bigger reef, so a tidal excursion doesn't always take you off the reef. Okay, so I've actually changed the colour bar to 6 too, so it's pretty much an order of magnitude greater residence time. So this reduces greatly the amount of reef cooling you'd have to do. And you can see in the reef cooling rate that still at the edges of the reef you have a large flux of cooling that you need to do. But that in the back of the reef, and maybe that's not where the corals are, but anyway, we'll take that on a bit later. In the back part of reefs where the waters come over and spend a long time on the reef, then you get a better, you don't have to cool as much over the whole reef to get the reduction in temperature at the particular location that you want. Okay, and so finally, just to show you Cockburn Reef, which is up past Lockhart River, and I chose this one because this one actually had one of the longest residence times, and the key to this one was that the way it was aligned was east-west, and in there the tidal stuff tends to be coming in that direction. So I guess the currents from the south weren't quite as dominant, and it went in the direction of the reef a little bit more, and that gave it quite a longer residence time. So there you can see getting a lot of the reef is up to 4 days. It gives you a much better chance to have an environmental, manipulation of change in temperature that would actually reside on the reef for long enough to feel that benefit. Okay, so this is just preliminary calculations, but it gives you an indication of where I'm going in trying to scope out which are the more effective reefs to put an intervention in there. And I think what will happen is engineers are going to come along and they're going to look at these numbers, they're going to find reefs that are better than others, they're going to innovate further. So for example, this is trying to cool the whole water column above a reef, but if you manage to get a density current that just sat cold water that flowed over the reefs, over the reefs themselves, not the full depth of water, and suddenly you're reducing the amount of cooling you've got to do. So I imagine that some of these assumptions will actually be conquered by innovations, and then we'll redo these and we'll see a better outcome. But for the moment anyway, it's a good example of optimising the reefs that I think we've got the best chance on. Okay, so just as a second thing with light stress, so this is a little bit more of a complicated one because of course to work out the effect of light we've got to go through the whole photophysiology of the symbiont in order to understand what the impact of reducing the light is. But anyway, possible interventions include shade cloths, reflective surface films, marine cloud brightening. Okay, so in the eReefs model, just to give you a really quick go, we've got a coral host. Sitting inside that is a symbiont. The symbiont has a pigment assemblage that's absorbing light. And there's a few processes like translocation and feeding, heterotrophic and autotrophic feeding. The key part to this for the bleaching process is in this slightly detailed diagram, but just the way to think of this, on the left we have all the pigments that are absorbing photons. Okay, the symbiont has a whole series of processes, it's called the xanthophyll cycle, by which it can dissipate heat, but when some photons are absorbed, they're passed on to what they call the reaction centres. This is the sort of location where pigments take in photons and do their different processes. The biochemists tend to think of these reaction centres as being either open, oxidised, you can see that, reduced, inhibited. The key thing is if they haven't had too much photons, then they can fix that carbon, they can use those photons to fix carbon, and then they've used the photons, no stress generated. However, if for some reason they can't fix the photons, then they start to close their reaction centres and eventually build up this reactive oxygen. So that's the bit at the bottom, and that is what we believe, and certainly is what's coded into the eReefs model, that's what we believe is driving the expulsion. So you might ask yourself in all of that, where did temperature come in? And the key thing is that the bit to take you from where it says Rubisco-mediated carbon fixation, if it gets too hot, that route closes down, and so therefore you build up more reactive oxygen. So to just give you a really quick summary, in the eReefs model, reactive oxygen stress builds up due to the amount of photons absorbed at high temperature. Okay, so it's all right to absorb photons if it's cool because you can use them, and if it's at high temperature, you're not building up light stress. But if you absorb photons at high temperature, then you start to build up your reactive oxygen. And so that's why I like to call it temperature-mediated light build-up of reactive oxygen. Okay, so we can now use this in the model to look at how we've got bleaching across the whole GBR. And so this is the 1 kilometre model. We ran it for the 2016 bleaching. This is to give you confidence that we can now use this for interventions. But what we've got here on the very left is the JCU aerial surveys, and then I've got the 1st of January, 1st of February, 1st of March and 1st of April 2016, and the colour bar on the right gives you coding from white, which means that it was too deep, so it didn't, in the model, so it didn't bleach, grey, no bleaching, and then increasing stress. And so you can see that although the colourings for the two different surveys actually are somewhat unrelated, if we qualitatively compare them, you can see that the eReefs model did quite a good job, especially on the inshore reefs, of getting the bleaching. Okay, and so we must have something, or I think we have something of that process of bleaching correct in the model, which we can now use to look at to see whether interventions work. And so here we go. What I've done is, so this is going back to the Cockburn Reef, and what we've got here is on the top we've got full sun for both, and there's the solar radiation. So obviously it's solar radiation at the seabed, so it's obviously very depth dependent. And then on the right we've got the reactive oxygen, so this is the stress building up. Okay, and so then some of these shading interventions can bring us down to say 70% of the solar radiation. And so when you achieve that, you can see, nice thing stopped. You can see that that with less solar radiation at the seabed, we build up less reactive oxygen stress. Okay, and so that was in Cockburn Reef, which we already felt we had a fairly good chance of doing an intervention that changed the water, that changed the temperature. But when it came to Davies Reef, okay, where now suddenly we've got much, we felt that the temperature intervention had very little chance because the residence time was so short. You can see the benefit that's gained there. So this one stopped at a particular point, but you can see that with reduced solar radiation, there was far less reactive oxygen stress, and therefore we hope less bleaching if we reduce the solar radiation by 30%. Okay, so so just to sort of sum up over this talk, I mean, this has only taken on some of the challenges. I think, certainly we're going to require some great maps to know which part of the reefs we want to save, to then consider, which parts of the reefs we want to save, and make sure that they're the ones that we're reducing the temperature on, not the bare sand that's sitting behind them, for example. Degree heating weeks, that's one measure of bleaching stress. It works some of the time, not all the time. I think there are people working on that in nest projects and stuff. I think that actually working out what is temperature stress that really affects the corals the most, and what the things that we want to target to reduce, I think that's going to be key. It's being done obviously by others. Even within the eReefs model, we've targeted one particular process that we believe is the bleaching, which is obviously the temperature-mediated, light-driven build-up of reactive oxygen. But are there other effects of temperature that can just get too hot, such that even if there wasn't a light stress, it would bleach? People have indicated that. I'm sure there's other processes that we're not including. So I think there's work to be done on even the fundamental or quantifying the underlying processes of bleaching to bring that through into the models so that we can optimise these interventions. And I think that will be just as true for people working on breeding corals. One example I like to make is that if we improve a coral's ability for its rubisco to work at a higher temperature, maybe we increase it by 1 degree, okay, then that'll save us for another 30 years, 50 years maybe, okay, but then we'd need to, of course, adapt further again, right? However, if we increase the ability of a coral to process reactive oxygen, okay, the sun's not about to get brighter. So it'd be a one-off intervention, a one-off change in the organism. So even that understanding, I think that fundamental understanding of the bleaching process is going to be important through all of the interventions that we're thinking about, because that's what we're really trying to avoid. And a few other sort of limitations there. So just to conclude, I think from the results I have, I can inform you that cooling loads are strongly dependent on residence time. It was sort of obvious anyway, but that it's reefs in low tidal energy areas with greater residence time, larger surface areas. These are the ones that we have a hope with temperature interventions. Smaller reefs, I think that the shading interventions are probably a better target. And finally, I think that you know, as these ideas go forward, it's going to be about optimising how we deploy them. I think that first go or first analysis is unlikely to be close to the optimal. It'll make the things look less feasible than they are. But I think as all of the people in this room start to think through the problems, the challenges there, innovate further, I think it's going to start to look more and more feasible. Thank you.
That's excellent, Mark. Thank you for that. That was fascinating. We have time for questions. Oh, we do have time. We haven't got much, but we'll have time for questions. Okay, I'll wait. Questions?
Yeah, I was just wondering, with the residence time on the reef, some of the ones you were sort of identified as being possible for interventions, is it sort of also possible that because of the high residence time on the reef, they're also more susceptible to local heating, you know, from the sun? So it might be that very reefs that appear to be good candidates are also suffer worse during you know, extreme temperature events because that water stays on the shallow reef for longer.
Yeah, exactly. And you probably saw some of in those high residence areas, you probably saw in the animation that actually got cooler as well in some of those spots. And the cooler bits, where it's obviously overnight, it follows that residence time thing as well, so the tracer. So, well, see, this comes down to the question of how have they adapted to what they are there at the moment, right? And so it's actually relating. So I did the temperature difference I did was back to a climatology, which is sort of, you know, like a 100-metre scale climatology, so it doesn't even recognise really the presence of the reef. In fact, there was probably no observation on that particular reef in that climatology, right? So how we even, I think the answer to your question is what's the temperature difference that we need to achieve related to the really local processes, and yeah, that's a challenge.
Yeah, that was fascinating talk. Thank you very much for that.